Hello everyone. Today we will study triple integrals. What is a triple integral? Before I define triple integral, let's review single integral and double integral first. Single integral from a to b f of x dx let represent area under the curve y equal to f of x from a to b. In order to find area under the curve, I divide the interval AB into small intervals and measure the width for each small interval, called delta SI. Next, on each subinterval, we pick sample point, called SI star. Then we plug in the sample point into function f. We have f of SI star. Then we use f of SI star to approximate the height of the rectangular region under the curve. Then I take base times height, that's the area under the curve on each subintervals. Then we add all area together, under the curve together. Since this area represents rectangular region under the curve, it's an approximate area. In order to find the actual area, take limit as the maximum delta SI approach to 0. That's the area under the curve. That's how we define single integral. For double integral, we think of volume under the surface. For double integral, we think of volume under the surface. Double integral f of sy over region R that represent volume under the surface z equal to f of sy over region R. In order to find the volume under the surface, we divide region R into small rectangular regions. Then we find the area for each rectangular region, called delta Aij. We find the area for each subregions, called delta Aij. Next, we pick sample point on each subregion, called Si star Yj star. Then we plug in each sample point into function f. We use this value to approximate the height of the rectangular solid under the surface. We use f of Si star Yj star to approximate the height of the rectangular solid under the surface. Then we take base area times height. That's the volume under the surface. Base area times height. That's the volume under the surface on each subregion. Then we add all this volume together. J from 1 to m. I from 1 to n. Since we use rectangular solid to approximate the volume, this is the approximate volume. In order to find the actual volume under the surface, we take limit as the maximum delta Si approach to 0 and maximum delta Yj approach to 0. That's the actual volume under the surface. Now, for triple integral, f of syz over a rectangular box B, we can first of all treat the function f as a density function. And then for this triple integral, we can consider this represent the mass of the rectangular box B. We can treat this triple integral as the mass of the rectangular box B. How do we find mass? In physics class, for a solid with uniform density. For a solid with uniform density, its mass can be found using the formula mass equal to density times volume. So in physics class, for any solid with uniform density, its mass can be found using the formula density times volume. Mass is always density times volume. The larger density, the more mass it is, and the larger volume, the more mass it is. Mass is defined by density times volume. Now, based on this formula, we try to find the mass of this rectangular box B. In order to find the mass of the rectangular box B, we first of all divide B into small boxes. Then we measure the volume for each small boxes, called delta Vijk. We divide B into small boxes. Then measure the volume for each small boxes, called delta Vijk. Then on each small boxes, we pick sample point, called Si star, Yj star, Z sub k star. On each subregion, we pick sample point. Then I can plug the sample point into function f. Since f represents density of these rectangular boxes, so I can use this sample point to approximate the density of each small rectangular boxes. We use this value f of Si star, Yj star, Zk star to approximate the density of each rectangular boxes. So by the physics law, density times volume is the mass of each rectangular boxes. Density times volume is the mass of each rectangular box. This is the mass of each small rectangular box. If I add every rectangular box together, if we add the mass of every rectangular box together, we can find the mass of this rectangular box B. If we add the mass of every small rectangle together, I find the mass of the total mass of this rectangular box B. So we can add them up. K from 1 to L. J from 1 to M. I from 1 to N. This is an approximate mass. Because for each rectangular box, for each small rectangular box, we only pick one point to be the sample. This is the approximate mass of this rectangular box B. In order to find the actual mass, we take a limit. Maximum delta Si goes to 0. Maximum delta Yj goes to 0. Maximum delta Z sub k goes to 0. And that's the definition of three-point integral. This is the definition of three-point integral. This is the definition of triple integral. So for triple integral, keep the following in mind. B represents a rectangular box. F of SYZ represents the density function over B. The triple integral represents the mass of the rectangular box B. So keep this idea in mind. That's how we define triple integral. Next, let me show you a picture. It will make more sense to you. It will make more sense to you. Consider B is a rectangular box. Let me draw the rectangular box first. Consider this is the rectangular box B. X is from A to B. Y is from C to D. Z is from E to F. Suppose this is rectangular box B. X is from A to B, Y is from C to D, Z is from E to F. So X is from A to B, Y is from C to D, Y is from C to D, and Z is from E to F. Z is from E to F. X is from A to B. Y is from C to D. Z is from E to F. So I first of all divide interval AB into n subintervals. So A will be x0, S1 is here, S2 is here. One of the slide in the middle will be xi minus 1. One of the partition will be si, x sub I minus 1. And this is si. And keep going. Last one, B is x sub n. Let me take out one slide from this box. Let's take out one slide from this box. A typical one is the one between si minus 1 and si. Let me take out one slide from this box. If I take out one slide from the box, if I take out this slide, it looks like this. I take out one slide from the box. This is from xi minus 1 to si. If we take out one slide, if I take out this slide here, the thickness of this slide, the thickness is delta si. It's between si minus 1 and si. The thickness is delta si. The thickness of this slide is delta si. The thickness of this slide is delta si. Since it's between, the thickness is between si minus 1 and si. The thickness is delta si. Now here we know that y is from C to D. Y is from C to D. Y is from C to D. Z is from E to F. Z is from E to F. Next, I divide interval CD into M subintervals. Next, I divide interval CD into M subintervals. So C will be y sub 0, y sub 1 here, y sub 2 here, y sub j minus 1 is here. Next is y sub j. D will be y sub m. D will be y sub m. So I take out one piece from this slide. I cut this slide into small strips. Cut this slide into small strips. I cut this slide into small strips. If I take this strip out, it looks like this. And this distance stays the same, it's delta Si. This distance here, this distance here will be delta yj, because it's between y sub j minus 1 and y sub j. So this distance here is delta y sub j. This distance is delta y sub j. And z is from E to F. Z is from E to F. Next, I will divide this interval E to F into K subintervals, into L subintervals. I'll divide the interval EF into L subintervals. So E represents Z sub 0. Z sub 1 is here. Z sub 2 is here. In the middle, we have Z sub K minus 1 here. Z sub K here. And keep going. F is Z sub L. If I take out this piece, here, it's a small rectangular box. If I take out this piece here, it's a small rectangular box. If I take out this piece here, it's a small rectangular box. Let me put it here. This side is delta Si, this side is delta y sub j, and this distance here is between Z sub k minus 1 and Z sub k. This distance here will be delta Z sub k. So we can see that the volume of this box, delta V I j k, is delta xi times delta yj times delta zk. That's how I find delta vijk. Delta vijk is delta si times delta yj times delta z sub k. That's how we find delta V of ijk. So delta Vijk represents the volume of each rectangular boxes. Delta Vijk represents the volume of each rectangular boxes. Next, for each rectangular boxes, we can choose a sample point called Si star, Yj star, Zk star. The sample point could be anywhere inside the box. Sample point could be anywhere inside the box, called Si star, Yj star, Zk star. Sample point could be anywhere inside the box. Choose a sample point for each rectangular box called Si star, Yj star, Zk star. Then since f represents a density function, if I plug in Si star, Yj star, Zk star, I find the density at this point. Then we use density at this point to approximate the density for this box. We use density at this point inside the box to approximate the density of this box. Then this is density of the box. This is the approximate density of this box. Density times volume by the physics law. Mass is always density times volume. If I use density times volume, I find the approximate mass for this rectangular box. Next, if I take the sum k from 1 to L, so k equal to 1, 2, 3, 4, 5 up to L, That's the total mass of this entire strip. If I take the sum k from 1 to L, I find the total mass of this entire strip. Then, if I take j from 1 to m, if I take the sum, let j from 1 to m. So when I take the sum k from 1 to L, I find the mass for this strip. If I take j from 1 to m, if I take the sum j from 1 to m, j equal to 1, j equal to 2, j equal to m, j equal to k, I find the sum of this entire slide. I find the total mass of this entire slide. If I take the sum, that j goes from 1 to m, I find the total mass of this entire slide. I find the total mass of this entire slide, which is the mass of this slide here. Then, next, if I take the sum, that I goes from 1 to n. If I take the sum, I goes from 1, 2, 3 up to n. I find the total mass of every slide together. The total mass of every slide together is the entire rectangular box. The total mass of every slide together is the total mass of this entire rectangular box. So that's an approximate mass of this rectangular box. This is an approximate mass. This represents approximate mass of this rectangular box. This is approximate mass, and this is called this is called the triple Riemann sum. This is called the triple Riemann sum. This is called the triple Riemann sum. This is an approximate mass of this rectangular box. In order to find the actual mass, we must take a limit. Take a limit that max delta Si goes to 0, max delta Si goes to 0, max delta Yj goes to 0, max delta Zk, max delta Z sub k goes to 0, which means I make each rectangular box very, very, very small. Then it will be the actual mass of this rectangular box. That's how we define triple integrals. That's how we define the triple integral. However, if we try to use this formula to compute triple integrals, it's very, very hard. It's very, very hard to take a limit here. So to make it a little easier, for a simpler version, we try to make each delta Si the same. We divide interval AB into n equal subintervals. We make delta Si the same everywhere. So we make delta Si equal to delta x. Make delta Si the same everywhere. Same thing. We make delta y the same everywhere. Make delta y the same everywhere. So make delta yj equal to delta y for all j. And similarly, we make delta z the same everywhere. So make delta zk equal to delta z for all k. If delta x, delta y, delta z is the same, then delta v will also be the same. Delta vij will be the same as delta v. So delta vij is also a constant. It's also the same everywhere. If they are all the same, if delta ijk is the same everywhere, we can set that delta v equal to delta v of ijk. And since delta x is the same everywhere, I can compute delta x using b minus a over n. Take the total length of the interval divided by number of subintervals. Delta y equal to d minus c over m. Take the total length divided by number of subintervals. Delta z equal to f minus e over L. So delta V can be rewrite as this times this times this. Delta X times delta Y times delta Z equal to B minus A over N times D minus C over M times F minus E over L. So this triple integral can be rewrite as a simpler version. A simpler version, this triple integral can be rewrite as limit n approach to 0, m approach to 0, approach to infinity. Limit n approach to infinity, m approach to infinity, and L approach to infinity. If n approach to infinity, delta S will be 0. If n approach to infinity, delta S will be 0. So maximum delta Si will be 0. If m approach to infinity, delta Y will be 0. So maximum delta Yj will be 0. If L approach to infinity, delta Z will be 0. So maximum delta Z will be 0. So this limit and this limit is equivalent. If we make every subinterval the same, then the summation stays the same. I from 1 to n, j from 1 to m, k from 1 to l. Now for the sample point, to make it easier, for sample point, I can use right upper corner. On each rectangular box, we can use the right upper corner. We can use right upper corner to be the sample point. So sample point will be xi, yj, zk. The sample point si star, yj star. So it's right upper corner in the front. For sample point, using the right upper corner in the front. For sample point, using the right upper corner in the front. So for the sample point, for each rectangular box, for each small rectangular box, choose the right upper corner in the front to be the sample point. Then if I choose this point to be the sample point, this point is Si, Yj, Zk. So the sample point Si star, Yj star, Zk star will be Si, Yj, Zk. So that's the new sample point. Then I can rewrite Si, Yj, Zk to be Si, Yj, Zk. That's the right upper corner in the front. That's the right upper corner in the front of the cube, of this cubit, of this rectangular box. Right upper corner in the front face. Right upper corner in the front face. This point is Si, Yj, Zk. In the front, Si. In the right is Yj. In the top is Zk. Si, Yj, Zk. That's the sample point. And delta V, Ijk, since it's the same everywhere, the volume of each rectangular box is the same everywhere. We can use delta V represent we can use delta V to represent the volume of each rectangular boxes. And delta V can be rewrite as B minus A over N, D minus C over M, F minus E over L. Let me put it here. That's a simpler version. Where delta V equal to delta X times delta Y times delta Z. Delta V equal to delta X times delta Y times delta Z. And delta X equal to B minus A over N. Delta Y equal to D minus C over M. Delta Z equal to F minus E over L. And SI, same as the single variable function, SI is A plus I delta X. Y sub j is the same as the double integral. Y sub j is C plus j delta Y. And Z sub k is E plus k times delta Z. That's a simpler version of the definition of triple integral. This is a simpler version. If we try to do calculation, use this formula, it will be a little easier. If we use this formula for calculation, it will be a little easier. That's a simpler version of the definition of triple integral. That's a simpler version. That's a simpler version of the definition of triple integral. Next, let's look at an example using the definition of triple integral. Let the solid B be defined as SYZ, point of SYZ in R3, where X is between 0 and 2, Y is between 0 and 3, and Z is between 0 and 4. Evaluate triple integral of xy plus xz over region B. Using the definition of triple integrals. If we use definition to evaluate triple integral, first of all, let me run a formula here. So let's compute delta V first. Delta V is delta x times delta y times delta z. Let's compute delta x, delta y, delta z first. Delta x is b minus a over n. 2 minus 0 over n, which is 2 over n. Delta y is d minus c over m. Delta z is f minus e over n. F minus c over L. F minus e over L, which is 4 over L. So delta V is delta x times delta y times delta z, which is delta x times delta y times delta z. That's 24 over nml. Next, we need to compute xi, yj, zk. X sub I is a plus I delta x. Here a is 0. I delta x is 2 over n. That's 2i over n. Y sub j is c plus I delta y. Here c is 0. So j delta y. J times delta y is 3 over m. So I got 3j over m. Z sub k is e plus k delta z, which is 0 plus k times 4 over L. That's 4L over k. So 4k over L. Then using the formula, we plug in 2i over n for x. We plug in 3j over m for y. We plug in 4k over L for z. So the triple integral can be rewritten as limit n goes to infinity, m goes to infinity, L goes to infinity, I from 1 to n, j from 1 to m, k from 1 to L. Replace x with 2i over n, replace y with 3j over m, replace x with 2i over n, replace z with 4k over L, times delta V. Delta V is 24 over nml. So let's simplify this part first. Distribute 24 nml into the parentheses. To make it easier, we can pull out 24. Distribute the denominator nml on the denominator. Pull out 24 first. If I pull out 24, I have limit n goes to infinity, m goes to infinity, L goes to infinity, I from 1 to n, j from 1 to m, k from 1 to L. Distribute denominator, we have 6ij over n square m square L plus aik over n square ml square. Let's evaluate the innermost summation first. Let's evaluate the innermost summation first. I first of all split this summation into two summations. For this sigma, k is the index, so we treat k as a variable. Everything other than k is a constant. The index is k. We only treat k as a variable. Everything other than k we treat it as a constant. So here there's no k. I pull everything outside. Write everything in front of the sigma. If everything was taken out, I write 1 here. Next summation, I keep k there. I pull everything other than k outside. We have ai over n squared ml squared sigma k from 1 to L of k. Then use the formula to find the summation. Use the formula. The sum of 1 from 1 to L is L. The sum of k from 1 to L is L times L plus 1 over 2. Then we simplify. I can cancel L from here. Cancel 1 over L from top and bottom. 8 divided by 2 is 4. So it can be rewritten as 24. 24 in the front, limit stays the same. Six ij over n squared m squared plus 4i times L plus 1 over n square m times L. Then we do the inner summation. Next we do the inner summation, j from 1 to m. I first of all split the summation into two summations. First one, j from 1 to m, 6ij over n square m square. The second one, j from 1 to m, 4i times L plus 1 over n square ml. Now here index is j. We only consider j is a variable. Everything other than j is a constant. We can pull constant outside the sigma. I keep j inside. Everything other than j I can pull it outside. I have 6i over n square m square. Take summation j from 1 to m. There's a j left here. For the second sigma, there's no j here, so we treat everything as a constant. Pull everything outside. If I pull everything outside, I write 1 inside. Next, evaluate each sigma. Six I over n square m square stays the same. If I take summation for j goes from 1 to m. That's m times m plus 1 over 2. M times m plus 1 over 2. 4i L plus 1 over n square times m times L. If I take the sum of 1, and j goes from 1 to m, that's m. Then I can cancel m from top and bottom. Cancel 1 of the m from top and bottom. 6 divided by 2 is 3. So if I simplify, I have I have 3i m plus 1 over n square m. N square m on the bottom. The second term is 4i L plus 1 over n square L. 4i L plus 1 over n square L. Next, we evaluate the outer sigma. I first of all split this sigma into two sigmas. I goes from 1 to n. First term, 3i times m plus 1 over n squared times m. Second term, I from 1 to n 4i times L plus 1 over n squared times L. Then evaluate each sigma individually. Here index is I. We keep I inside. We treat everything other than I as a constant, put it outside. We treat everything other than I as a constant, we can put it outside. Here I can pull out 3m plus 1 over n squared m, I from 1 to n of 3i of I. Second term, I can pull out 4 times L plus 1 over n squared L, I from 1 to n of I. Then use the formula. We have 3 times m plus 1 over n squared m. Sigma of I goes from 1 to n. This is n times m plus 1 over 2. Sigma of I from 1 to n is n times m plus 1 over 2. If we simplify, it can be, I can cancel one of the n from top and bottom. 4 divided by 2 is 2 on the top. So if I simplify, I have 3 on the top, 2 on the bottom, m plus 1, m plus 1 on the top, m times n on the bottom. For the second term, we have 2 on the top, L plus 1, m plus 1 on the top, n times L on the bottom. Then it can be rewrite as (3 over 2 times 1 plus 1 over m times 1 plus 1 over n plus 2 times 1 plus 1 over L times 1 plus 1 over n. If we take a limit as n goes to infinity, m goes to infinity, L goes to infinity, that's 0, that's 0, that's 0, that's 0. The final answer is 24 times 3 over 2 times 1 times 1 plus 2 times 1 times 1. If I distribute 24, I have 36 plus 48. The final answer is 84. It doesn't look too simple. It's doable, but it doesn't look too simple. Is there an easier way? Is there an easier way to compute triple integral? An easier way to compute triple integral is called Fubini's theorem. We have Fubini's theorem for 3 variables. We have Fubini's theorem for triple integrals. A simpler way is we can use Fubini's theorem. Next, let me introduce Fubini's theorem. Fubini's theorem for triple integral. Let B be a rectangular region. Let B be a rectangular box. Rectangular box is B equal to SYZ, the set of SYZ in R3, where X is between A and B, Y is between C and D, and G is between E and F. Let B be a rectangular box. Suppose f of syg, a three-variable function f of syg, is continuous on B. Suppose f is continuous on B, then the triple integral f of syg over region B can be written as outer integral from A to B, the middle integral from C to D, the inner one is from E to F, f of syg dg dy dx. It can be written in any orders. dx, dy, dg can be written in any orders as long as the boundary matches. G must be between E and F. Y must be between C and D. X must be between A and B. As long as the boundary matches, it can be written in any orders. That's the Fubini's theorem for triple integral. Let's redo the previous problem using Fubini's theorem. Let's redo the previous problem using Fubini's theorem. The previous problem, we're looking for triple integral over region B, xy plus xz dv, where B is a rectangular box, like x between 0 and 2, y is between 0 and 3, z is between 0 and 4. So use Fubini's theorem, we have integral x between 0 and 2, y is between 0 and 3, z is between 0 and 4, sy plus xz dg dy dx. So we start from the innermost integral. For the innermost integral, we keep the outer integral the same. So keep x equal to 0, x equal to 2 the same, y equal to 0, y equal to 3 the same. Take antiderivative for the inner integral. Take antiderivative with respect to z. If I take antiderivative with respect to z, I treat s and y as constant. So take antiderivative for sy. If sy is a constant, antiderivative is syg. For antiderivative of constant, take the constant, multiply by the variable. Next term, xz. If I take antiderivative, it will be xz squared over 2. And evaluate g from 0 to 4. dy dx. Then evaluate the inner integral. If I substitute 4 for z, I have 4sy If I substitute 4 for z, we have 16. 4 squared is 16. 16 over 2. 16 over 2 is a. If I substitute 0, I get 0. If I substitute 0 for z, both terms are 0. Next, we have a double integral here. We do the inner integral first. Take antiderivative with respect to y. So I keep outer integral the same. Take antiderivative with respect to y. We have 2x y squared. Y squared over 2 times 4 is 2. Y squared over 2 times 4x is 2x times y squared. Take antiderivative with respect to y. If there's no y here, as is constant. Antiderivative of constant is the constant times the variable. Now evaluate y from 0 to 3 dx. Next, we plug in 3 and 0, take difference. X is from 0 to 2. I plug in 3 and 0, take difference. If I plug in 3 for y, 3 squared is 9. 9 times 2 is 18. If I plug in 3 for y, 3 times 8 is 24. If I substitute 0, I get 0. Combine like terms. This integral can be rewritten as 42x. If I take antiderivative with respect to x, I have 21x squared. Evaluate from 0 to 2. If I substitute 2, I get 84. If I substitute 0, I get 0. So the answer is 84. We get exactly the same thing, but using Fubini's theorem, it will be much easier. Using Fubini's theorem, it will be much easier. In general, Fubini's theorem not only works for triple integrals over a rectangular box, it also works for triple integrals over some different solid. Next, let me show you Fubini's theorem in general. Fubini's theorem in general also works for triple integrals over some special solid. Let me introduce the type 1 solid. Type 1 solid looks like this. Consider a solid. It has an upper cover. It has an upper surface, it's called upper cover. It has a surface on the top. It has a lower cover. It has a surface on the bottom. Consider a solid. It has an upper surface. It's bounded by an upper surface and a lower surface. Let's call the lower surface z equal to u1 of sy. Let's call the upper surface z equal to u2 xy. Assume the solid E is bounded by its two surfaces, u2 on the top, u1 on the bottom. And assume the edge of solid E are formed by vertical lines perpendicular to SY plane. Assume the edge of the solid are formed by vertical lines perpendicular to the SY plane. Assume this is solid E. It has the upper cover, lower cover. The upper surface is z equal to u2 of sy. Lower surface z equal to u1 of sy. Let me draw this solid in standard coordinate system. That's the x-axis. That's the y-axis. That's the z-axis. Now, if we look at the picture from top to bottom, we can see the projection of the solid in the xy plane. If we look at the picture from top to bottom, all we can see is this surface here. Because the edges are vertical line perpendicular to xy plane, we won't be able to see anything on the edge. All we can see is this surface. That's called the projection in the xy plane. That's called the projection in the xy plane. What we can see the solid from top to bottom is called the projection in the xy plane. Let's call this region D in the xy plane. So for the type 1 solid, let E be the solid of S, Y, Z. Let E formed by the points S, Y, Z in R3, where point SY belongs to region D. And Z coordinate is bounded by the lower surface U1 of SY and upper surface U2 of SY, where D is the projection of solid E in the SY plane. Assume function f of s, y, z is continuous on E. Assume function f of s, y, z is continuous on E. Then, by Fubini's theorem, the triple integral f of s, y, z over solid E. The triple integral f of s, y, z over solid E can be rewritten as the double integral over the projection D, dA, that's an outer integral. The inner integral is the integral z from the lower surface to the upper surface f of s, y, z dz. That's the inner integral. So using Fubini's theorem, I can rewrite the triple integral as a double integral with a single integral inside. That's Fubini's theorem for type 1 solid. Next, let me introduce type 2 solid. Type 2 solid looks like this. Consider a solid. It's bounded by two surfaces, one on the left, one on the right. Consider a solid. It's bounded by two surfaces, one on the left, one on the right. Assume on the left side, it's bounded by a surface. Called y equal to u1 of x comma z. Assume on the left side is bounded by a surface u1 equal to y equal to u1 of x comma z. On the right side is bounded by a different surface. Called y equal to u2 of xz. On the left side is bounded by the surface y equal to u1 of sc. on the right side is bounded by a surface y equal to u2 of st. And the surface on the side are formed by horizontal lines. The surface on the side are formed by horizontal lines perpendicular to the xz plane. The surface on the side are formed by horizontal lines perpendicular to the xz plane. Consider this solid here. On the left side is bounded by the surface y equal to u sub 1 xc. On the right side is bounded by the surface y equal to u sub 2 xc. Let me draw this solid in a standard coordinate system. X, Y, Z. That's an x-axis, y-axis, z-axis. This is called the solid E. On the left side is bounded by the surface y equal to u1 sc. On the right side is bounded by the surface y equal to u2 xc. Then, if you look at the picture from right to left, the projection, we can only see this surface. If you look at the picture from right to left, we can only see this surface. That's called the projection of this solid E. And the projection in the xy plane looks like this. Projection in the xz plane looks like this. Projection in the xz plane. That's the projection of this solid in the xz plane. If you look at the picture from right to left, we can only see this surface, because all the edges are perpendicular to the xz plane. The edges are perpendicular to the xz plane, so we won't see anything. We can only see this surface here. That's called the projection. That's the projection in the xz plane. Let's call this region D. Let's call this region D in the xz plane. Let's call this region D in the xz plane. So let E. Next, let me give you the formula for Fubini's theorem. Fubini's theorem over this type 2 solid. Let E be the set of points of S, Y, Z in R3, where XZ, point of SZ in SZ plane, or points XZ belongs to region D, and Y is between the left surface and the right surface. Y is bounded by the left surface U1 S comma Z, right surface U2 S comma Z. That's the solid D, where D is the projection of solid E. D is the projection of solid E in the xz plane. If you look at the picture from right to left, all we can see is this surface. This surface is the projection in the xz plane. From right to left, all we can see is this surface. This surface is a projection in the xz plane. Assume f of syz is continuous on E. Assume f of syz is continuous on E. Then if we apply Fubini's theorem, for solid E, triple integral of f of syz dv over the solid E. If we apply Fubini's theorem for type 2 solid, for this solid E, it can be written as the double integral over region D, double integral over region D in the SC plane, dA, that's an outer integral. The inner integral is integral y from lower to upper, from left to right, y from left to right, y from u1xc to u2xc, f of s, y, z, dy. That's the Fubini theorem for type 2 solid. That's the Fubini theorem for type 2 solid. Next, let me introduce type 3 solid. Consider a solid is bounded in the front and back by two surfaces. Consider a solid is bounded in the front and back by two surfaces. Assume the surface is bounded in the back by the surface S equal to u1 of yz. In the front, it's bounded by the surface in the front is bounded by the surface S equal to u2 of yz. Let's consider a solid E. In the front, it's bounded by the surface x equal to u2 of yz. In the back, it's bounded by it's bounded by the surface s equal to u1 of yz. And assume the surface on the side are formed by vertical lines. Assume the surface on the side are formed by vertical lines perpendicular to the yz plane. Assume the surface on the side are bounded by horizontal lines perpendicular to the yz plane. That's the surface on the side. Assume the surface on the side are bounded by the surface. Assume the surface on the side are bounded by. Assume the surface on the side are formed by horizontal lines perpendicular to the yz plane. That's the surface on the side. It's formed by horizontal lines perpendicular to the yz plane. That's the front surface. That's the surface in the front. That's the surface in the back. Let me draw this solid. Let me draw this solid E in the standard SYZ plane. SYZ. If you look at the picture from the front to the back, if you look at the picture of this direction, from the front to the back, all we can see is this surface. We won't see anything on the side because this surface is formed by horizontal lines perpendicular to YZ plane. So if you look at the solid in this direction, all we can see is this surface. All we can see is this surface. That's called the projection in the YZ plane. That's called the projection in the YZ plane. That's the projection in the YZ plane. That's the projection in YZ plane. Let's call this region D. So D is the projection of solid E in the YZ plane. So that's the type 2 solid. That's the type 3 solid. That's the type 3 solid. So for type 3 solid, let me show you the Fubini theorem for type 3 solid. Let E be the set of points of SYZ in R3, where YZ belongs to region D. YZ are points. YZ are points belong to region D in the YZ plane. And X is bounded by the back surface and the front surface. Back surface is U1 YZ. Front surface is U2 YZ. So YZ are points in region D in YZ plane. X is bounded by two surfaces, S equal to U1 of YZ, S equal to U2 of YZ. That's solid D. That's solid E. That's solid E. Where D is the projection of E. D is the projection of solid E in the YZ plane. Assume function f Assume f of SYZ is continuous on the solid E. Then the general Fubini theorem for type 3 solid. The general Fubini theorem for type 3 solid looks like this. The triple integral f of SYZ over solid E can be rewritten as double integral over the region D in the YZ plane. That's an outer integral. That's an outer double integral. The inner integral, X is bounded by U1 of YZ. X is bounded by U1 of YZ and U2 of YZ. F of SYZ dx. That's the Fubini theorem for type 3 solid. That's the general Fubini theorem for type 3 solid. The proof of general Fubini theorem is very similar as the proof we learned in chapter 12.2 when we are learning Fubini theorem, general Fubini theorem for double integrals. The proof for general Fubini theorem for triple integrals is very similar as the proof for Fubini theorem for double integrals in chapter 12.2. The proof is very similar. Next, let's do some examples for triple integrals. How do we evaluate this triple integral? Outer integral from 0 to 1, middle integral from 0 to 1, inner integral from 0 to 1, s squared plus y squared plus z squared, dz, dy, dx. How do we solve this integral? We start from the inner integral first. Keep the outer the same. Start from the inner integral first. Take antiderivative with respect to z. We have x squared z. We treat s as constant. Constant. When we take constant, when we take integral for constant, take a constant multiplied by the variable. x squared z plus y squared z plus z raised to power 3 over 3 evaluate z from 0 to 1, dy dx. If we substitute 1 for z, we have x squared plus y squared plus 1/3. If we substitute 0 for z, we get 0, dy dx. Next, we solve the inner integral with respect to y. Solve the inner integral with respect to y. That means I treat s as constant. I have x squared y plus y to the power 3 over plus 1/3 of y. Evaluate from 0 to 1, y from 0 to 1. Next, we substitute 1 for y. Substitute 1, substitute 0 for y, then subtract. If we substitute 1 for y, we have x squared plus 1/3 plus another 1/3, which is 2/3. Next, we take antiderivative with respect to x, which is x to the power 3 plus 2 over 3x. Evaluate from 0 to 1. If we plug in 1, we get 1/3 plus 2/3. If we plug in 0, I get 0. 1/3 plus 2/3 is 1. So the answer is 1. Next example. Double integral, triple integral. The outer one is from -1 to 1. The middle integral is from 0 to 1. The inner integral is from 0 to 2. X plus y plus z dy dx dz. So we take the inner integral first, then do the outer integral. The innermost integral is dy. We take antiderivative with respect to y. Leave the outer integral the same. Take the antiderivative with respect to y. We have sy plus y squared over 2 plus zy. Evaluate y from 0 to 2. Dx dz stays the same. Then I plug in 2 for y, plug in 0 for y, then subtract. If we plug in 2 for y, we have 2x plus 4 plus 2z. If we plug in 0 for y, we get 0. Dx dz. Then take the inner integral with respect to x. Integral from -1 to 1. Take antiderivative with respect to x. We have x squared plus 4x plus 2xz. Evaluate x from 0 to 1 dz. Then keep the outer integral the same. Substitute 1 for x, substitute 0 for x, then subtract. If we substitute 1 for x, we have 1 plus 4 plus 2z. If we substitute 0, we get 0. So this integral can be rewritten as 5 plus 2z dz. Then we take antiderivative with respect to z. We have 5z plus z squared. Evaluate z from -1 to 1. If we substitute 1, we have 5 plus 1. If we substitute -1, we have -5 plus 1, which is 6 minus -4. So the answer is 2 is 10. Next example. Outer integral is from 1 to e. The middle integral is from 1 to e squared. The inner one is from 1 to e cubed. 1 over x, y, z. Dx, dy, dz. Let's observe this integral first. For the integrand here, 1 over syz, it can be rewritten as 1 over x times 1 over y times 1 over z. That's a function of x times the function of y times the function of z. And all the boundaries here are constants. All the boundaries are constants. In this situation, we can apply a property of integral. In this situation, we can apply a property of integral. Let me introduce a property of integral. For triple integral with constant boundaries, a to b, c to d, e to f, if the integrand can be written as a product of f of x, g of y, h of z, if the integrand can be written as a product of f of x, g of y, h of z, then this triple integral can be split into 3 single integrals. This triple integral can be split into a product of 3 single integrals. Integral x from a to b, function of x, f of x dx, times function of y is from c to d, g of y dy, times integral of z is from e to f, h of z dz. We calculate each integral individually, then multiply together. For a triple integral with constant boundaries, and the integrand can be written as a product of function of x, function of y, function of z, then we can split the triple integral into the product of 3 single integrals. We calculate each integral individually, then multiply out. So keep this idea in mind. The proof for this is very similar as the proof we learned for double integral. The proof is very similar as the proof we learned for double integrals. Keep this in mind. The proof of this property is very similar as the proof for double integral with the same property. Let's continue with number 3. So here we can see that all boundaries are constant, and we can write the integrand as a product of function of x, function of y, function of z. So I can split this triple integral into 3 single integrals. X is from 1 to e cube, 1 over x dx. Y is from 1 to e squared, 1 over y dy. Z is from 1 to e, 1 over z dz. Then we solve each integral individually, then multiply out. For the first integral, we have ln of x, evaluate from 1 to e cube. The second one, we have ln of y, from 1 to e squared. The third one, we have 1 of ln of z, evaluate from 1 to e. If we evaluate the first integral, I plug in e to the power 3. ln of e to the power 3 is 3. ln of 1 is 0. If we plug in e squared, ln of e squared is 2. ln of 1 is 0. If we plug in e, ln of e is 1. ln of 1 is 0. So the final answer, 3 times 2 times 1 is 6. Next example. Triple integral. The outer one is from 0 to 3. The middle one is from 0 to square root of 9 minus s squared. The inner one is from 0 to square root of 9 minus s squared. dz, dy, dx. If there's no integrand, we assume the integrand is 1. If there's nothing inside, we assume the integrand is 1 here. So we start from inner, work from inner to outer. From inner, if we take antiderivative with respect to z, keep an outer the same. Antiderivative of dz is z. Evaluate z from 0 to radical 9 minus s squared, dy dx. Keep an outer integral the same. If we substitute z equal to radical 9 minus s squared, we have radical 9 minus s squared. If we substitute 0, we get 0. dy dx. Then we do the inner integral. Inner integral, we take antiderivative with respect to y. Take antiderivative with respect to y. With respect to y, we treat this as a constant. We treat 9 minus s squared as a constant. So take antiderivative with respect to y. We have radical 9 minus s squared times y. Antiderivative of constant is a constant multiplied by the variable. Evaluate y from 0 to radical 9 minus s squared. Then I plug in radical 9 minus s squared for y and plug in 0 for y. Take the difference. If I plug in radical 9 minus s squared for y, we have radical 9 minus s squared multiplied by itself, which is 9 minus s squared. If I substitute 0 for y, I get 0. Then take antiderivative with respect to x. I have 9x minus s cubed over 3. Evaluate from 0 to 3. If we plug in 3, we get 27 minus 27 cubed is 3 cubed is 27. 27 divided by 3 is 9. If we substitute 0, we get 0. 27 take away 9 is 18. Next example. Outer integral from 0 to 1. The middle one from 0 to 1 minus s squared. The inner one from 3 to 4 minus s squared minus y. Integrand is x. dz, dy, dx. So we start from the inner integral first. Keep an outer the same. 0 to 1, 0 to 1 minus s squared. If you take antiderivative with respect to z, we have xz. Evaluate z from 3 to 4 minus s squared minus y. dy dx. Then substitute z. Z is 4 minus s squared minus y. If I substitute 3 for z, we have 3x. dy dx. Let me simplify the integrand first. Distribute x, I have 4x. 4x minus 3x is x. Distribute x, we have s cubed. Distribute x, I have minus sy. Take antiderivative with respect to y. I have s squared over 2 minus x to the power 4 over 4 minus s squared over 2 times, take antiderivative with respect to y. No x. That's xy minus s cubed times y minus xy squared over 2. Evaluate from 0 to 1 minus s squared dx. If we substitute 1 minus s squared for y, let me write it here. Y equal to 0, y equal to 1 minus s squared. If we substitute 1 minus s squared for y, we have x times 1 minus s squared minus s cubed times 1 minus s squared minus x over 2 times 1 minus s squared dx. Then simplify. Distribute x. I have x minus x to the power 3. Distribute s cubed. I have s cubed plus x to the power of 5 minus, if I expand the perfect square here, I have 1 minus 2s squared plus x to the power of 4. Distribute s over 2. We have x over 2 plus s cubed minus x to the power of 5 over 2 dx. Then take antiderivative, then combine like term first. Combine like term first. X to the power of 5 minus x to the power of 5 over 2 is half of x to the power of 5. S cubed, positive s cubed, negative s cubed get cancelled. We have minus s cubed. X minus s over 2 is half of x dx. Then we take antiderivative with respect to x. Half of x to the power 6 over 6 minus x to the power 4 over 4 plus half of x squared over 2. Evaluate x from 0 to 1. If we substitute 1, we have 1 over 12 minus 1 over 4 plus 1 over 4. If we substitute 0, we get 0. So the final answer is 1 over 12. Number 6. Evaluate the triple integral of sy over the solid E, where E is a set of points sy, z in R3, where x is between 0 and 2, y is between 0 and 4, z is between the surface z equal to 0 and z equal to s plus y. So this is a type 1 solid. This E is a type 1 solid. For type 1 solid, if we use Fubini's theorem, the inner integral is z equal to 0, z from 0 to s plus y. Integrand is sy stays the same. dz. Then for the outer integral, we have a double integral over the region D, dA. What's region D here? Region D is a projection in the xy plane. In the xy plane, we have x between 0 and 2, y between 0 and 4. That's the projection in the xy plane. This is region D. Since this is a rectangular region, the order of s and y doesn't matter. Since this is a rectangular region, the order of s and y doesn't matter. I can take x first. Since this is a rectangular region, since D is a rectangular region, the order of integral doesn't matter. I can take x from 0 to 2, y from 0 to 4, z from 0 to s plus y, s times y, dz, dy, dx. Then we evaluate the triple integral. Do the inner integral first. Take antiderivative with respect to z. We have s, y, z. Evaluate z from 0 to s plus y. If we substitute s plus y for z, we have xy times s plus y. If we substitute 0, we get 0. dy dx. Simplify the integrand. I have s squared y plus sy squared dy dx. Next, we take antiderivative with respect to y. We have x squared y squared over 2 plus xy to the power 3 over 3. Evaluate y from 0 to 4. Then evaluate x from 0 to 2. If we substitute 4 for y, 4 squared is 16. 16 over 2 is a. We have as squared. If we substitute 4 here, 4 to the power 3 is 64. We have 64 over 3x. If we substitute 0 for x, for y, we get 0. Next, take antiderivative with respect to x. We have ax to the power 3 over 3. Plus 64 over 3 times x squared over 2. Evaluate from 0 to 2. If I substitute 2, 2 to the power 3 is a. A times a is 64. I get 64 over 3. If I substitute 2 here, 2 squared is 4. 4 divided by 2 is 2. 2 times 64 is 128. 64 plus 128 is 192. 192 divided by 3 is 64. So the answer is 64. Number 7. Evaluate the triple integral of sy over E, where E is the solid region bounded by the paraboloid cylinders y equal to s squared and s equal to y squared, and the planes z equal to 0 and z equal to s plus y. So first of all, let's draw the 3D picture first. Let's draw the solid region E first. Solid region E is bounded by the paraboloid cylinder y equal to s squared and s equal to y squared. Let's draw their projection in the SY plane first. In the SY plane, y equal to s squared is a parabola. And s equal to y squared is also a parabola. That's the region inside both paraboloid cylinder. And bounded by two planes, z equal to 0 and z equal to s plus y. Z equal to 0 is an SY plane. That's this SY plane. Z equal to s plus y. Z equal to s plus y. That's a plane. At this point, at the intersection of these two graphs, s must be 1, y must be 1. If we plug in 1 for x, plug in 1 for y. If we plug in 1 for x, plug in 1 for y, z must be 2. So let's not solve it here. We can see that the upper surface is z equal to s plus y. Is this plane here? Upper surface is z equal to s plus y. Lower surface is z equal to 0, the xy plane. D, region D is this region here. The projection in the xy plane. That's region D. Region D is this region here in xy plane. Let me draw region D in the xy plane. Region D in the xy plane is bounded by two parabolas. The lower curve is y equal to s squared. Upper curve is x equal to y squared. This is region D in the xy plane. If we try to take an integral for region D, we can either integrate from bottom to top or left to right. In general, we prefer to integrate from bottom to top. If we try to integrate from bottom to top, we try to write y in terms of x. So s equal to y squared, that means y can be written as y equal to radical x. So it can be rewritten as y from s squared from lower to upper, y from s squared to radical x. X, the projection in the x-axis is from 0 to 1, the projection of this graph. If we look at this region from top to bottom, we only see this graph. This graph in the x-axis is the line segment from 0 to 1. If you push this graph down to x-axis, it's a line segment from 0 to 1. So x is from 0 to 1. Y is from s squared to radical x. Z is from 0 to s plus y. X, y, dz, dy, dx. Then, when we solve the integral, we solve from inner to outer. If we solve the inner integral, take antiderivative with respect to z, we have s, y, z. Evaluate from z equal to 0 to z equal to s plus y. dy, dx stays the same. Then substitute z equal to x plus 1, z equal to 0. If we substitute z equal to x plus 1, if we substitute z equal to s plus y, that's sy times s plus y. If we substitute 0 for z, we get 0. dy, dx. If we simplify, we have x squared y plus xy squared dy dx. Next, we take antiderivative with respect to y. X from 0 to 1. Take antiderivative with respect to y. We have x squared y squared over 2 plus xy to the power 3 over 3. Evaluate y from s squared to radical x. Dx stays the same. If we substitute radical x, radical x squared is x times s squared is s cubed. If we substitute radical x squared, radical x cubed radical x cubed is x raised to 3 half. X raised to 3 half times x is x raised to 5 half. If we substitute x squared, x squared is x to the power 4. X to the power 4 times x squared is x to the power 6. If we substitute x squared here, x squared to the power 3 is x raised to power 6. X raised to power 6 times x is x raised to power 7. This integral can be rewritten as integral from 0 to 1. Let's put in descending order. 1/3, negative 1/3 of x to the power 7 minus x to the power 6 over 2 plus x to the power 3 over 2 plus x to the minus x to the half of x to the power 6 plus half of x to the power 3 plus 1/3 of x to the power of 5 over 2 dx. Next, we take antiderivative with respect to x. Take antiderivative with respect to x. We have x to the power 8 over 8 minus 1 over 2 x to the power 7 over 7 plus 1 over 2 x to the power 4 over 4 plus 1/3 x to the power of 7 over 2 divided by 7 over 2, which means multiplied by the reciprocal 2 over 7. Evaluate from 0 to 1. If we substitute 1, we have negative 1 over 24 minus 1 over 14 plus 1 over 8 plus 2 over 21. I get 3 over 28 using calculator. I get 3 over 28. Number 8. Evaluate the triple integral sine y over the solid region E, where E is the solid region below the plane z equal to x and above the triangular region in the xy plane with vertices 0, 0, 0, pi 0, 0, 0, pi 0. So first step, in order to set up a triple integral, let's draw the solid region first. Let's draw solid region E first. Let's draw the solid region E first. E is a solid below the plane z equal to x and above the triangular region in the xy plane with vertices 0, 0, 0, pi 0, 0, 0, pi 0. That's the triangular region in the xy plane. 0, 0, 0, pi 0, 0, 0, pi 0. And below the plane z equal to x. Z equal to x. That's a plane going through origin. And z equal to x, when s is pi, z is also pi. When s is pi, z is also pi. So this is a plane. This is a plane. Z equal to x. That's the upper surface. Lower surface is the xy plane. Lower surface is the xy plane, z equal to 0. And the projection in the xy plane is this triangle. The projection in the xy plane is this triangle. That's region D in the xy plane. That's the projection. The projection is this triangle in the xy plane. This is region D. So that's the type 1 solid. If we set up the type 1 solid, we have z from 0 to x. The lower surface is z equal to 0. Upper surface is z equal to x. The function is sine y dz. Then we take double integral over region D dA. Double integral over region D dA. This is region D. Let me draw region D in the xy plane. Region D in the xy plane, it goes through pi in the x-axis. It goes through pi in the y-axis. That's the triangular region D. This is the triangular region D. We can try to integrate from bottom to top. The bottom is the line y equal to 0. X-axis is y equal to 0. The top is this straight line. This line goes through 2 points. Slope is rise over long. Pi over pi is 1. The line is going down. The slope is negative 1. Y-intercept is pi. So y is negative x plus pi, which can be rewrite as pi minus x. That's an upper bound. That's a lower bound. That's a lower curve. That's an upper curve. We integrate from bottom to top. And projection in the x-axis. The projection in the x-axis is a line segment from 0 to pi. So x is from 0 to pi. Y is from 0 to pi minus x. Z is from 0 to x. Sine y dz dy dx. Then take the inner integral. Take antiderivative with respect to z. We have sine y times z. Evaluate z from 0 to x. Dy dx. Next, substitute x, substitute 0. If we substitute x, we have x sine y. If we substitute 0, we get 0. Dy dx. Next, we evaluate the inner integral. Take antiderivative with respect to y. Antiderivative of y is cosine. Antiderivative of sine y is negative cosine y. Y is from 0 to pi minus x. X from 0 to pi. If we substitute pi minus x, we have cosine pi minus x. If we substitute 0, cosine 0 is 1. This integral can be rewrite as x minus x times cosine pi minus x. What's cosine pi minus x? What's cosine pi minus x? cosine pi minus x. If we use the formula for cosine, we know cosine of a plus b is cosine a cosine b minus sine a sine b. Cosine of a minus b is cosine a cosine b plus sine a sine b. If we plug in into this formula, we have cosine pi cosine x plus sine pi sine x. Cosine pi is -1. Cosine x, for cosine x we leave it the way it is. Sine pi is 0. And we know 0 times sine pi, 0 times sine x is 0. -1 times cosine x is negative cosine x. So cosine pi minus x is negative cosine x. Cosine pi minus x is negative cosine x. Substitute here. I write this x in the front plus negative x times negative cosine x is also positive. That's x cosine x. S cosine x dx. Then solve this integral. For the first part, it's easy. That's x squared over 2. For the second part, x cosine x, we need to use integration by parts. For s cosine x, we need to use integration by parts. Let u be x, let dv be cosine x dx. du is dx. If you take derivative for u, du is dx. Take antiderivative for cosine, we get positive sign. So use the formula u times v, x sine x minus v times du, integral of sine x dx. Take antiderivative for sine x, we have negative cosine x, double negative become positive. So take antiderivative for x cosine x, we have x sine x plus cosine x. Evaluate from 0 to pi. Evaluate from 0 to pi. If we substitute pi, we have pi squared over 2 plus pi times sine pi is 0, plus cosine pi is -1. If we substitute 0, we have 0 plus 0 times sine 0 is 0, cosine 0 is 1. So we have pi squared over 2 minus 1, which is pi squared over 2 minus 2. So the answer is pi squared over 2 minus 2. Next example, find the volume of the solid region between the paraboloid cylinder g equal to y squared and the xy plane, and bounded by planes s equal to 0, s equal to 1, y equal to -1, y equal to +1. The volume formula for triple integrals is defined as volume of solid region E equal to the triple integral of 1 over the solid region E dv. That's how we define the volume formula. The reason we define the volume formula this way is because for any triple integral, f of syz over solid region E dv, by definition of triple integral, we define f of syz as the density function of the solid region E. We define f of syz as the density function of the solid region E. In this formula, f of syz is 1. In this expression, the density function f of syz is 1. If the density function is 1, that means this solid E has uniform density. So the solid E has uniform density. That means the density is the same everywhere. It has uniform density. Since it has uniform density, the mass of E is the density. Since it has uniform density, the mass of E is the density times the volume. Since E has uniform density, mass of E is density times volume. And since the density function is 1 here, mass of E is 1 times the volume of E. Based on this formula, we know that the mass of E and the volume of E has the same value. The mass of E and the volume of E has the same value. So the mass of E is triple integral. Mass of E is the triple integral of E. Triple integral over E. Mass of E is the triple integral of 1 over E dV. And the volume of E is E of E. That's why we define the volume of E to be the triple integral of 1 over the solid E. Next, let's try to draw. In order to take an integral, we need to draw the solid region E first. Solid region E is bounded by paraboloid cylinder. Is between the paraboloid cylinder z equal to y squared and sy plane, bounded by these 4 planes. Let's draw these 4 planes in sy plane first. Let's draw these 4 lines in the sy plane first. In the sy plane, these 4 planes represent lines. In the sy plane, these 4 planes represent 4 lines in the sy plane. S equals 0, S equals to 1. Say 1 is here. One is here. Y equal to -1, y equal to 1. Y equal to 1, y equal to -1. That's the projection of these 4 planes in the sy plane. It's a rectangle in the sy plane. Next, we try to draw the paraboloid cylinder z equal to y squared. Paraboloid cylinder z equal to y squared. So the region below the cylinder, below the paraboloid cylinder, above xy plane is the solid E. The region below the solid region, below the paraboloid cylinder, above xy plane is the solid region E. We can see that here. The paraboloid cylinder is the upper surface. Lower surface is xy plane. So lower surface is xy plane, z equal to 0. Upper surface is a paraboloid cylinder, z equal to y squared. Now the projection in the xy plane. For the projection in the xy plane, if you look at the picture from top to bottom, all we can see is this rectangular region. All we can see is this rectangular region in xy plane. So x is from 0 to 1. Y is from -1 to 1. That's the region D in the xy plane. That's region D in the xy plane. Then, since this is a rectangular region, the order of x and y doesn't matter. This is a rectangular region. The order of x and y doesn't matter. So I take x from 0 to 1, y from -1 to 1. Z is from 0 to y squared. Integrand is 1. We have dz, dy, dx. Usually we prefer an order dz, dy, dx. That's natural. We prefer an order dz, dy, dx. We find a projection from top to bottom. Then in xy plane, integrate from bottom to top. Find projection from top to bottom. That's a little easier. Next, we solve the inner integral first. Take antiderivative with respect to z. Antiderivative of 1 is z. Z is from 0 to y squared. dy, dx. Substitute y squared, substitute 0. Let's check, we get y squared. dy, dx. Next, take antiderivative with respect to y. We have y to the power 3 over 3. Evaluate from -1 to 1 dx. If I substitute 1, I get 1/3. If I substitute -1, I get -1/3. That's 2 over 3 dx. Take antiderivative with respect to x. We have 2 over 3x. Evaluate from 0 to 1. If we substitute 0, we get 0. If we substitute 1, we get 2/3. So the answer is 2/3. Next example, find the volume of the solid region inside both cylinders, x squared plus y squared equal to 1, and x squared plus z squared equal to 1. Find the volume of the solid region inside both cylinders. Solid region inside both cylinders. X squared plus y squared equal to 1. That's a cylinder parallel to the z-axis. X squared plus z squared equal to 1. That's a cylinder parallel to y-axis. How is their intersection looks like? Their intersection the intersection looks like this. If we take it out, it looks like this. This surface is the equation s squared plus y squared equal to 1. This surface here is the cylinder s squared plus y squared equal to 1. It's very hard. If we try to solve it directly, it's very hard. It's very hard to draw the region, and it's very hard to find the bound, to find the upper and lower bound. It's very hard. So if we finding the entire solid, it's very hard. Let's try to find the solid in the first arctan first. In the first arctan, that's a region that all S, Y, Z are positive. Find the volume of the solid in the first arctan first, and there are 8 arctans. Multiplied by 8, we can find the volume of this solid. Find the solid in the first arctan first, then multiply by 8, we can find the solid of this object. So let's draw the solid in the first arctan. In the first arctan, that's the region S is positive, Y is positive, and Z is positive. There are 8 different arctans, 3 planes, 3 coordinate planes, divide the space, 3 coordinate planes, divide the space into 8 different arctans. First arctan is a region that S positive, Y positive, Z positive. Let's draw this cylinder in the first arctan. S squared plus Y squared equal to 1. It looks like this in the first arctan. It's a quarter of a cylinder in the first arctan. It's a quarter of a cylinder in the first arctan. This is a cylinder S squared plus Y squared equal to 1. That's the cylinder in the first arctan. Let me draw this cylinder in the first arctan. S squared plus Z squared equal to 1. That's the cylinder S squared plus Z squared equal to 1 in the first arctan. Now, how do they intersect? How does these two cylinders intersect? Their intersection looks like this. That's their intersection. Let me remove those unnecessary curve. You can see their intersection looks like this. That's the intersection of two cylinders in the first octane. That's the intersection of two cylinders in the first octane. This surface is a cylinder S squared plus Y squared equal to 1. This surface is a cylinder S squared plus Z squared equal to 1. So from top to bottom, we can see that that's the upper surface. Lower surface is SY plane. Lower surface is SY plane. This is the upper surface. Lower surface is SY plane. So for upper surface, I need to get Z by itself. Z is radical 1 minus S squared. For upper surface, I must get Z by itself. So lower surface is Z equal to 0. Upper surface is Z equal to radical 1 minus S squared. The volume is 1. Volume formula is triple integral of 1 over solid E dV. So the integrand is 1 times dz. For the outer integral, we take double integral over region D times dA. Region D, if you look at the picture from top to bottom, all we can see is this surface. We won't be able to see the other cylinder. All we can see from top to bottom, all we can see is this surface. And the projection of this surface in the SY plane is this quarter of a circle. It's this quarter of a circle. It's a quarter of a circle in the SY plane. That's region D. That's this quarter of a circle in the SY plane. Since this quarter circle is bounded by the cylinder S squared plus Y squared equal to 1, since this quarter cylinder is bounded by the cylinder S squared plus Y squared equal to 1, this curve here is S squared plus Y squared equal to 1. Now we can try to take integral from bottom to top. The bottom curve is x-axis y equal to 0. The top curve, we need to get y by itself. Y equal to square root of 1 minus s squared. That's the bottom curve. That's the top curve. And if we find a projection, this radius is 1. If we find a projection in the x-axis, it's from 0 to 1. This circle has radius 1. If we find a projection in the x-axis, we have a line segment from 0 to 1. So x is from 0 to 1. Y is from 0 to radical 1 minus s squared. That's a lower curve. That's an upper curve. Projection in the x-axis is a line segment. It's a line segment from 0 to 1. Z is from 0 to radical 1 minus s squared. 1 times dz, dy, dx. Next, we solve the inner integral first. Take antiderivative for 1 with respect to z. I get z. Z is from 0 to radical 1 minus s squared, dy, dx. substitute z equal to radical 1 minus s squared, I get radical 1 minus s squared. If I substitute 0, I get 0. Next, take antiderivative with respect to y. So the entire expression is a constant. I have radical 1 minus s squared times y. Y is from 0 to radical 1 minus s squared times dx. Then I substitute the upper limit and lower limit. If I substitute the upper limit, I have radical 1 minus s squared. Radical 1 minus s squared times radical 1 minus s squared. Square root get cancelled. We have 1 minus s squared. If I substitute 0, I get 0. Then take antiderivative with respect to x. I have x minus s cubed over 3. From 0 to 1. If we substitute 1, we have 1 minus 1/3. If we substitute 0, we get 0. 1 minus 1/3 is 2/3. So that's the volume in the first octane. That's the volume of the solid in the first octane. That's the volume of this solid in the first octane. And we know there are 8 different solids. We know there are 8 different solids. In the space, there are 8 solids. So the total volume is is 2/3 times 8. That's the volume in the first octane. And we know there are 8 different octanes. 3 coordinate plane cut the 3-dimensional space into 8 different octanes. That's the volume in the first octane. To find the total volume, take this volume, multiply by 8. The answer is 16 over 3. Next example, find the volume of the solid region bounded by the planes x plus z equal to 1 and y plus 2z equal to 2 and the coordinate planes in the first octane. Find the volume of the solid region bounded by these 2 planes and the coordinate plane in the first octane. Let's draw the first octane first. Coordinate plane means xy plane, yz plane, and xz plane. They are called coordinate planes. In the first octane, that's a region that x, y, z, they are all positive. xy plane, xz plane, and yz plane. These 3 planes, they are called coordinate planes, bounded by these 3 planes in the first octane. Let's draw these 2 planes first. X plus z equal to 1. X plus z equal to 1 here. Y is missing. I can write z as 1 minus x. This is a line. This is a line in the xz plane. This is a line in the xz plane. We don't need this. This is a line in the xz plane. If I substitute 0 for x, z is 1. If we substitute 0 for z, x is 1. Connect 2 points, we can make a line. Since y is missing, I can shift this line over to make the plane. Since y is missing, so this plane here, this plane is x plus z equal to 1. This plane is x plus z equal to 1. Now how about this plane here? Y plus 2z equal to 2. In this plane, x component is missing. Let's draw a line in the yz plane first. In this equation, x is missing. Let's find a line in the yz plane first. If I substitute 0 for z, y is 2. If we substitute 0 for z, y is 2. Let me make the first plane a little bigger. Then we can see the intersection of these two planes. That's the first plane. That's the first plane. The second plane, when z is 0, y is 2. When y is 0, z is 1. And since x is missing, I can shift this line in the direction of in x direction. That's the plane. That's the plane. Y plus 2z equal to 2. This is a plane y plus 2z equal to 2. This plane here represents y plus 2z equal to 2. This plane represents x plus z equal to 1. This plane represents y plus 2z equal to 2. How do they intersect? The intersection looks like this. That's their intersection. This number here is 2. This number here is 1. Let me remove these unnecessary lines. This surface here is x plus z equal to 1. This surface is x plus z equal to 1. This surface here is y plus 2z equal to 2. This surface is x plus z equal to 1. This surface is y plus 2z equal to 2. If we look at the picture from top to bottom, what can we see? From top to bottom, we can see these two surfaces, and their projection is this rectangle in the xy plane. From top to bottom, we can see these two surfaces, and their projection is this rectangle in the xy plane. Let me draw the projection in the xy plane. It's a rectangular region that goes through 1 in the x-axis and goes through 2 in the y-axis. Next region D. Next region D. It's a rectangular region in the xy plane. Now, how about this line? How about this line? If we try to find the projection of this line in the xy plane, this line satisfies both equations. It's the intersection of these two planes. It satisfies both equations. If we try to find the projection in the xy plane, if we try to find the projection of this line in the xy plane, we try to solve these two equations together. Try to eliminate z. Try to eliminate z. Write x and y together. We can find this line, the projection of this line in the xy plane. So I try to put these two equations together, eliminate z. For the first equation, I can get z by itself. Z equal to 1 minus x. Then I can substitute z into the second equation. I have y equal to y plus 2 times 1 minus x equal to 2. If I simplify, I have y plus 2 minus 2x equal to 2. Cancel 2, I get y equal to 2x. I get y equal to 2x. So y equal to 2x is the projection of this line in the xy plane. Y equal to 2x is the projection of this line in the xy plane. That's here. This line is y equal to 2x. And this surface here, this surface is here. This surface is z equal to 1 minus x. This surface is z equal to 1 minus x. If we get z by itself here, z is 2 minus y over 2. This surface here is this surface. If you look at the picture from top to bottom, this surface is this triangle in the xy plane. If I solve an equation for z, if we look at projection from top to bottom, we need to get z by itself. Z is 1 minus y over 2. So this surface is z equal to 1 minus y over 2. If we try to solve the integral, if we try to set out the integral, since we have two upper surfaces, from top to bottom we have two upper surfaces, we need to set up two integrals. Since we have two upper surfaces, we must set up two integrals. First integral, look at this triangle here. Look at this surface. Upper surface is z from 0 to 1 minus x, 1 times dz. Let's call this region D1. Call this region D2. Double integral D1. I'm taking double integral over this region D1. dA plus the other region, the other surface is over D2, this surface is over region D2 in the xy plane. Lower surface is xy plane z equal to 0, upper surface is z equal to 1 minus y over 2, 1 times dz. dA. We must compute each integral individually. First integral, region D1 here. Lower curve is y equal to 0. Lower curve is y equal to 0. Upper curve is y equal to 2x. X is from 0 to 1. X is from 0 to 1. Lower curve is y equal to 0. Upper curve is y equal to 2x. Z is from 0 to 1 minus x. 1 dz dy dx. Second integral, we take integral over region D2. For region D2, lower curve is y equal to 2x. Upper curve is y equal to 2. This horizontal line going through 2 in the y-axis. Upper curve is y equal to 2. Lower curve is y equal to 2x. Projection of this region in s-axis is also from 0 to 1. This point goes to 1. This point goes to 0. The line, region in the middle, goes to region between 0 and 1. So the projection in the s-axis is a line segment from 0 to 1. Lower curve is y equal to 2x. Upper curve is y equal to 2. Lower surface is z equal to 0. Upper surface is 1 minus y over 2. 1 times dz, dy, dx. Next, let's evaluate this integral here. First integral, take antiderivative with respect to x. With respect to z, I have z evaluate from 0 to 1 minus x, dy, dx. If I substitute 1 minus x, I get 1 minus x. If I substitute 0, I get 0, dy, dx. If I take antiderivative with respect to y, I have 1 minus x. One minus x times y. Y from 0 to 2x. If I substitute 2x for y, I have 1 minus x times 2x. If I substitute 0, I get 0. Then distribute. I have 2x minus 2x squared. Take antiderivative. We have s squared minus 2s cubed over 3. Evaluate from 0 to 1. If I substitute 1, I have 1 minus 2/3. If I substitute 0, I get 0. 1 minus 2/3 is 1/3. So first integral gives 1/3. The volume under this surface is 1/3. The volume under the second surface, let me solve it here. If I take antiderivative with respect to z, I have z here. Evaluate from 0 to 1 minus y over 2. dy, dx. If I substitute 1 minus y over 2 for z, I get 1 minus y over 2. If I substitute 0, I get 0. So I keep dy, dx the same. Next, take antiderivative with respect to y. I have integral from 0 to 1. Take antiderivative with respect to y. I have y minus y squared over 4. Evaluate from 2x to 2 times dx. Substitute 2x. If I substitute 2, I get 2. 2 squared is 4. 4 over 4 is 1. If I substitute 2x, I have 2x minus 2x squared is 4s squared. 4s squared over 4 is s squared dx. If we combine like term here, we have s squared minus 2x plus 1 dx. Take antiderivative. We have x to the power 3 over 3 minus s squared plus x. Evaluate from 0 to 1. If I substitute 1, I have 1/3 minus 1 plus 1. If I substitute 0, I get 0. 1/3 minus 1 plus 1 is 1/3. So the final answer, 1/3 plus 1/3 is 2/3. This method If we find a volume from top to bottom, it's very hard. Is there a better way to solve this problem? In order to find a better way to solve this problem, let me draw this solid region over. Let's try to find the projection in different planes. So far, we always try to find projection in xy plane. Let's try to find projection in different planes. Let's try to consider this solid region is a type 2. It's a type 2 solid. Let's try to consider this solid region as a type 2 solid. We try to find a left side surface and a right side surface. In this direction, from right to left, we can see that the left side surface is this triangle. The left side surface is this triangle in the XZ plane. The left side surface is this triangle in the SC plane. This can be written as y equal to 0. For left side surface and right side surface, we must write y in terms of x and z. For left side surface and right side surface, we must write y in terms of s and z. So the left side surface is the plane, is the triangle in the SC plane. We write it as y equal to 0. The right side surface is this plane here. This plane can be represented by the equation y plus 2z equal to 2. If I write y in terms of x and z, I can write this plane as y equal to 2 minus 2z. So that's the left side plane, that's the right side plane. So for type 2 solid, the inner integral is y from lower to upper. Take a double integral over region D. D is a projection in the XZ plane. So here, I take double integral of D. D is here. Y from left to right. Lower limit is y equal to 0. Upper limit is y equal to 2 minus 2z. Integral is 1. We are doing dy. Then take double integral over region D. D is the triangular region in the XZ plane. D is the triangular region in the XZ plane. Let me draw it here. Let me draw region D in the XZ plane. That's XZ plane. D is a triangle that goes through 1 in the x-axis and goes through 1 in the z-axis. This is region D in the SZ plane. We can see that the lower curve is z equal to 0. This is XZ plane, so we write lower curve is z equal to 0, not y equal to 0. It's z equal to 0. Upper curve is this line. This line has slope. This line has going through 1 and 1. It has slope -1. Y-intercept is 1. It can be rewritten as y equal to 1. Sorry. Here, z represent y. Here, z represent y. In XZ plane, z represent y. It should be z equal to -x plus 1. Slope is -1. Y-intercept is 1. And it can be rewritten as 1 minus x. lower curve is z equal 0, upper curve is z equal to 1 minus x. Projection in the x-axis is a line segment from 0 to 1. Projection in the x-axis is a line segment from 0 to 1. Projection in the x-axis is a line segment from 0 to 1. So here, x is from 0 to 1. Z is from 0 to 1 minus x. Y is from 0 to 2 minus 2z. Integral is 1. dy, dz, dx. It must match here. dy, dz, dx. Then solve the integral first. X from 0 to 1. Z from 0 to 1 minus x. Take antiderivative with respect to y. We have y. Y is from 0 to 2 minus 2z. dz, dx. If we substitute y is 2 minus 2z, we have x from 0 to 1. Z is from 0 to 1 minus x. If we substitute, we have 2 minus 2z. If we substitute 0, we get 0. Next, take antiderivative with respect to z. X is from 0 to 1. Z is from 0 to 1 minus x. Take antiderivative with respect to z. We have 2z minus z squared. Z minus z squared. Z is from 0 to 1 minus x. Then substitute. X is from 0 to 1. If I substitute z is 1 minus x, I have 2 times 1 minus x minus 1 minus x squared. If we substitute 0, we get 0. Simplify. Integral from 0 to 1. Distribute 2, we have 2 minus 2x minus 1 plus 2x minus s squared dx. If we combine like terms, let me put it here. We have 1 minus 2x and plus 2x cancel. 2 minus 1 is 1. Minus 2x and plus 2x cancel. Minus s squared dx. Take antiderivative. Take antiderivative. We have x minus x over x cubed over 3. Evaluate from 0 to 1. If we substitute 1, we get 1 minus 1/3, which is 2/3. We get exactly the same answer. But using this technique, we only solve one integral. If we find projection in the SC plane, we only solve one integral, which is much quicker than this way. Now here we find a projection in SY plane, XZ plane. Can we set out the integral by finding projection in YZ plane? Can we set out the integral by finding projection in YZ plane? If you look at the picture this way, if you look at the picture this way, let's consider type 3 solid. We try to find a surface in the front, a surface in the back. For type 3 solid, we try to find a surface in the front and surface in the back. Then find a projection in the YZ plane. That's for type 3 solid. If we consider this is a type 3 solid, we try to find a surface in the front, a surface in the back. Then we try to find the projection in the YZ plane. Let's consider this is a type 3 solid. So The surface in the front is this surface. This surface is x plus z equal to 1. This surface is x plus z equal to 1. So for type 3 solid, we must write, for each surface, we must write x in terms of yz. For each surface, for type 3 solid, we must write the front surface and the back surface as x in terms of y and z. X in terms of y and z. So this surface here is x plus z equal to 1. If I get s by itself, this surface can be represented by x equal to 1 minus z. This surface can be represented by s equal to 1 minus z. The surface on the back is this triangle in the yz plane. The first surface in the back is this triangle in the yz plane. So for this surface, we have x equal to 0. For this surface, for this triangle in the SC plane, in the yz plane, we have s equal to 0. So the surface in the front is s equal to 1 minus z. Surface in the back is s equal to 0. Integral is 1 dA. Integral over the region D in the yz plane. YZ plane, we have this triangle. That's a projection in the YZ plane. This triangle is a projection in the YZ plane. Sorry, this is dx. We have dA outside. Then let's look at the projection in the YZ plane. In the YZ plane, we have a line segment. Going through 1, going through 2. That's the region D in the YZ plane. This triangle is bounded by this surface. Y plus 2z equal to 2. This triangle is bounded by this surface. Y plus 2z equal to 2. In this plane, z actually represents y. Y represents x. Actually, z represents y. Y represents x. Usually we write x here, write y here. But this is YZ plane. So y represents x. Z represents y. So the lower curve is clearly z equal to 0. Usually it's y equal to 0, but here z represents y. So lower curve is z equal to 0. Upper curve is this triangular region. But this triangular region is bounded by this surface. So it must satisfy this equation, y plus 2z equal to 2. If I solve this equation for z is 1 minus y squared. So that's an upper surface. Or you can use these 2 points. You can use these 2 points to find equation of a line. The slope is rise over long, 1 over 2. It's going downward, negative 1 over 2. Y-intercept is 1. You can get the same answer. You can either use this equation, or you can use these 2 points to find the equation here. Z equal to 1 minus y over 2. This region is bounded by this surface. This triangular region is bounded by this plane. We can use the equation of this plane to find equation of this line here. Or you can use these 2 points to find equation of a line. We get the same answer. So for z, the lower bound is z equal to 0. Upper bound is z equal to 1 minus y over 2. X is from 0 to 1 minus z. Now the projection in the y-axis is from 0 to 2. One times dx times dz times dy. That's a different way to solve this problem. If we treat the solid as type 3 solid, that's how we set out the integral. Now, if you solve this integral correctly, you must get the same answer as what we did. before, you must also get 2/3. So verify by yourself. If you solve it correctly, you must also get 2/3. Next example, evaluate the triple integral of SYZ over the solid region E, where E is a solid region inside the tetrahedron vertices 0, 0, 0, 1, 0, 0, 1, 1, 0, 1, 0, 1. A tetrahedron is a solid that has 4 vertices and 4 faces. A tetrahedron is a solid that has 4 faces, 4 vertices and 4 faces. That's called tetrahedron. It's a solid which contains 4 vertices and 4 faces. It's called tetrahedron. It has 4 vertices and 4 faces. That's called tetrahedron. Now, let's draw the solid region first. It's a tetrahedron with 4 vertices here. 0, 0, 0, 1, 0, 0, 1, 1, 0, 1, 0, 1. Let's draw the solid first. Let's draw the solid region first. Zero, 0, 0 is in the origin. 1, 0, 0, that's the point in the x-axis. 1, 0, 0. 1, 1, 0. S coordinate is 1, y coordinate is 1, z coordinate is 0. S coordinate is 1, y coordinate is 1. This is a point 1, 1, 0. 1, 0, 1. S coordinate is 1, z coordinate is 1. It's here. S coordinate is 1, z coordinate is 1. That's the point 1, 0, 1. So we have 4 points here. 1, 1, 2, 3, 4. Connect 4 points, we can make tetrahedron. That's a tetrahedron with 4 vertices, 4 faces. First face, second face, third face, 4th face on the bottom. That's a tetrahedron with 4 faces, 4 vertices and 4 faces. If we look at the picture from top to bottom, consider this is a type 1 solid. Look at the picture from top to bottom. This plane is an upper surface. Lower surface is this triangle in the SY plane. If we consider this is a type 1 solid, from top to bottom, we can see that this is the upper surface. Lower surface is this triangle. The equation for the lower surface is this triangle located in the SY plane, so it's z equal to 0. Equation for the lower surface is z equal to 0. How about the upper surface? How do we find the equation for this upper surface? How do we find this equation? How do we find the equation for this upper surface? This surface, to find this surface is not easy. This is a surface going through 3 points. This is a surface going through 3 points. 0, 0, 0, 1, 1, 0, 1, 1, 0, 1, 0, 1. This surface going through 3 points. Passing through 3 points, we need to find the equation of this plane. Let's find the equation for this plane. Let's find the equation for this plane. This plane contains 3 points. This plane contains 3 points. Let's call point P is 0, 0, 0. Point Q is 1, 1, 0. Point R is 1, 0, 1. This plane contains 3 points, P, Q, R. Connecting 2 points, we can make a vector. Let's find vector PQ and vector PR first. Vector PQ, take head minus tail. Q minus P is 1, 1, 0. Then find vector PR. Again, head minus tail, R minus P. We get 1, 0, 1. Now we know two vectors on the plane. If I take a cross product, I can find a normal vector on the plane. If I find a cross product, I can find a normal vector in the plane. So let's take a cross product. I, J, K. First vector is 1, 1, 0. Second vector is 1, 0, 1. Take cross product. That's 1, 0. I times 1, 0, 0, 1 minus J times 1, 0, 1, 1 plus K times 1, 1, 1, 0. Take determinant. I have I times 1 minus 0. J times 1 minus 0. K times 0 minus 1, which is vector 1, negative 1, negative 1. That's the normal vector. Since I know the normal vector, equation of a plane is 1 times x minus x naught. Let's call this point x naught, y naught, z naught. X minus x naught minus 1 times y minus y naught minus negative 1 times z minus z naught equal to 0. If we simplify the equation, we have x minus y minus z equal to 0. So this plane can be represented by the equation x minus y minus z equal to 0. This plane can be represented by the equation x minus y minus z equal to 0. Since we consider this is an upper surface, we need to get z by itself. Since we consider this is a type 1 solid, we try to integrate from lower surface to upper surface. We must get z by itself. Z is y minus x. If we solve for z is s minus y. Z is s minus y. If we solve this equation for z is s minus y. So that's an upper surface. Lower surface is sy plane, z is 0. So we have z from 0 to x minus y, syz times dz. Projection in the sy plane. Projection in the sy plane is this triangle. Projection in the sy plane is this triangle. Projection in sy plane is this triangle. This triangle goes through 0, 0 in the sy plane. It goes through 1 in the s-axis. It goes through 1, 1 in the sy plane. This is sy plane. So lower surface is lower line. This is region D. Lower curve is y equal 0. This is region D. This is region D in the sy plane. Lower curve is y equal 0. Upper curve is a line going through 0, 0 and 1, 1. Y-intercept is 0. This is straight line. Y-intercept is 0. Slope is 1. Rise over 1, 1 over 1. Slope is 1. So this line is y equal to x. So lower bound is y equal to 0, upper bound is y equal to x. Now if we find a projection in the x-axis, we have a line segment from 0 to 1. So x is from 0 to 1. Y is from 0 to x. Z is from 0 to s minus y. We have s, y, z, dz, dy, dx. Then solve the integral from inner to outer. S is 0, x is from 0 to 1, y is from 0 to x. Solve the inner integral. Take antiderivative with respect to z. We have s, y times z squared over 2. Z is from 0 to x minus y. dy, dx. If we substitute y minus z, we have sy times y minus z squared over 2 times x minus y squared over 2. If we substitute 0 for z, we get 0. Let me simplify this integral here. I can pull out half. I have sy times s squared minus 2sy plus y squared dy dx. Pull out half. S is from 0 to 1. Y is from 0 to x. Distribute sy. We have x to the power 3y minus 2s squared y squared plus xy to the power of 3 dy dx. Then take antiderivative with respect to y. Take antiderivative with respect to y. I have x to the power 3 times y squared over 2 minus 2s squared times y to the power 3 over 3 times x plus x times y to the power 4 over 4. Evaluate y from 0 to x dx. If we substitute x for each y, we have half times x to the power 5 minus 2/3 times x to the power 5 plus 1/4 times x to the power 5 dx. If we combine like terms, half plus a quarter is 3/4. 3/4 minus 2/3. 3/4 minus 2/3 is 1 over 12. Take antiderivative. We have 1/2 times 1 over 12 times x to the power 6 over 6. Evaluate from 0 to 1. If we substitute 1, we have 1 over 144. That's the answer. Next, in the previous example, set up the integral in 5 different ways. What does it mean, 5 different ways? We know for triple integral, dv can be written as dx times dy times dz. But I can put dx, dy, dz in different orders. I can write it as dx, dz, dy, dy, dx, dz. dy, dz, dx, dz, dx, dy, or dz, dy, dx. We can write 3 components in 6 different orders. So there are totally 6 ways to set up integral. We can consider the integral as type 1 solid, type 2 solid, type 3 solid. And for each type of solid, we can set our integral in 2 ways. Together, there are 6 ways to set our integrals. So there are 6 different orders. In the previous problem, we already set up in one of the orders. dz, dy, dx. There are 5 other orders. To set it up. Let's try to set up integral in different orders. We already have an order with dz, dy, dx. Let's set it up in a different order. Let's try this order first. dz. Let me keep dz the way it is. Let's swap dx and dy. Let's try this order. Let's try to set our integral in this order. dz, dx, dy. Which means we keep the integral the same. For region D, we try to switch order for s and y. If dx comes first, if ds comes first, we must take integral for this line. For region D, take integral from left to right. If we take integral from left to right, we must write x in terms of y. If I switch order for s and y, in the previous example, take integral from bottom to top. Now if we switch order, take integral from left to right. If we take integral from left to right over region D, we must write x in terms of y. So this line y equal to x, if I write x in terms of y, it can be rewritten as s equal to y. The right bound, the curve on the right side curve is s equal to 1. This is a vertical line going through 1 in the x-axis. This is s equal to 1. Then the projection in the y-axis. If I push the entire graph into y-axis, this point goes to 1. This point goes to 1 in the y-axis. This point goes to 0 in the y-axis. And the region in the middle go to the point between 0 and 1. So the projection in the y-axis is a line segment from 0 to 1. Y is from 0 to 1. Left side curve is s equal to y. Right side curve is s equal to 1. And the inner integral stays the same. Because we take find the projection in the same direction. Inner integral stays the same. Z equal to 0. Z equal to x minus y. S y z. dz, dx, dy. So that's a different order. That's a different order to set out the integral. Next, in order to set our integral in different ways, we must consider this solid as type 2 solid. Let's consider this solid as type 2 solid. Let's consider this solid region as type 2 solid. Let me draw this solid over. This plane is x minus y minus z equal to 0, this plane. This point is 1, 1, 0. This point is 1, 0, 1. If we consider this is a type 2 solid, we need to find out the left side surface and the right side surface. Left side surface, we can see that if we look at the picture from right to left, we can see that left side surface is this triangle in SC plane. Left side surface is this triangle in the SC plane. And for left side and right side surface, we must write y in terms of x and z. So this triangle in ST plane can be written as y equal to 0. That's the right side. That's the left side surface. Right side surface, if we look at the picture in this direction, we can see that the right side surface still is this plane. If I try to write y in terms of x and z, this plane can be written as y equal to x minus z. So it can be set up as y from 0 to x minus z. Integrand stays the same. Integrand stays the same. dy. Take double integral over region D, where D is the projection in the SC plane. D is the projection in the SC plane, which is this triangle. D is the projection in the SC plane, which is this triangle. This triangle in SC plane, it goes through 1 in the x-axis. It goes through 1, 1 in SC plane. And it goes through origin, it touches origin. So this is region D. This triangle is this triangle here. This is XC plane, Y. Actually, Z represents Y. So this line, lower curve is Z equal to 0. If you integrate from bottom to top, lower curve is Z equal to 0. Upper curve, this line, slope is 1. Y-intercept is 0, slope is 1, so it's Z equal to X. So lower curve is Z equal to 0. Upper curve is Z equal to X. Y stays the same. Lower curve is Z equal to 0. Upper curve is equal to X. Then X, if we find a projection in the x-axis, we have a line segment from 0 to 1. If we push the entire graph down to s-axis, if we push the entire graph down to s-axis, we have a line segment from 0 to 1. So x is from 0 to 1. dx. So that's a different way. Another way, if we try to switch order for dx and dx and dz, we try to take integral for this region D. We try to take integral from left to right. From left to right, we try to write x in terms of z here. We are in the xc plane. Try to write x in terms of z. So left side curve can be rewritten as s equal to z. Right side curve is s equal to 1. Then if we push the entire graph into z-axis, we can see that this point goes to 1 in the z-axis. So the entire region becomes the line segment in the z-axis from 0 to 1. So z is from 0 to 1. X is from left bound is s equal to z. Left bound must come first. Left bound is s equal to z. Right bound is s equal to 1. and the inner integral stays the same. The inner integral stays the same. Y is from 0 to x minus c syz dy dx dz. That's a different way to set it up. Next, for another different way, we try to treat this solid as a type 2 solid. Next, for another way to set it up, we try to treat this solid as a type 3 solid. Let me draw the picture over. Let me draw the solid over. It goes through 1 in the x-axis. That's the point 1, 1, 0. It goes through the point 1, 0, 1 in SC plane. And it goes through origin. This plane is x minus y minus c equal to 0. Now, if we consider this is a type 3 solid, we need to find out what's the front surface, what's the surface in the front, what's the surface in the back. So we can clearly see that for this solid, surface in the front is this plane. This is a plane parallel to YZ plane passing through 1 in the x-axis. So this plane is s equal to 1. This plane is s equal to 1. Now, the plane in the back, if you look through this solid this way, the plane in the back is this plane here. The surface in the back is this plane here. And for surface in the back, we must write x in terms of y and z. For surface in the back, we must write x in terms of y and z. So get s by itself. S equal to y plus z. So if I set up this way, I have inner integral x. The back plane comes first. The back plane is the lower bound. The front plane, the plane in the front is the upper bound. The plane in the back is the lower bound. So the lower bound is s equal to y plus z. Upper bound is s equal to 1. Integrand is syz dx. Then we have double integral over region D, dA. D is the projection. D is a projection in the YZ plane. If you look at the solid this way, this point goes to 1 in the z-axis. This point goes to 1 in the y-axis. This line is a line segment here. So the projection is this triangle here. The projection in the YZ plane is this triangle. This point goes to 1 in the z-axis. This point goes to 1 in the y-axis. So this triangle is the projection in the YZ plane. If you look at the picture this way, this triangle is the projection in the YZ plane. In this direction, we can only see this triangle. And this triangle in the YZ plane looks like this. So let me draw the projection here. Projection region D in the YZ plane is a line segment that goes through 1 in the z-axis and goes through 1 in the y-axis. That's region D in the YZ plane. Now let's try to integrate from bottom to top first. From bottom to top, lower curve is y is z equal to 0. Here z represents y represents x. Lower curve is z equal to 0. This line is a line segment going through 1 in the z-axis. So the slope is negative 1. Y-intercept is also 1. This line is negative 1 y plus 1. Slope is negative 1. Y-intercept is 1. It can be rewritten as z equal to 1 minus y. So z inner integral stays the same. X is from y plus z to 1. Z is from 0 to 1 minus y. If we push the entire graph down to the y-axis, we have a line segment from 0 to 1. So y is from 0 to 1. The inner integral stays the same. X is from y plus z to 1. Integrand stays the same. SYZ dx dz dy. That's a different way to set out the integral. That's a different way to set out integral. Another way, if we switch order, if we try to take integral from left to right, for region D, if we take integral from left to right, left side curve is the curve, is this curve, y equal to 0. This is a vertical line, y equal to 0. And for right side curve, I must write y in terms of x. Y is 1 minus x. If I solve this, y is 1 minus c. Y is 1 minus c. If I get y by itself, y is 1 minus c. So that's left side curve, that's right side curve. If I find a projection in the z-axis, this point goes to 0. The entire line segment goes between 0 and 1. We have a line segment between 0 and 1. If we push this triangular region into z-axis, we have a line segment from 0 to 1. So z is z-axis. Z boundary for z is from 0 to 1. The boundary for y, from left to right, left comes first, is from 0 to 1 minus c. And the inner bound stays the same. X is from y plus z to 1. Integrand is SYZ dx dy dx dy dz. So that's how we set out the integral in 5 other ways. Now, if you verify each integrals, if you compute each integrals and solve it correctly, you must all get the same answer. You must all get 1 over 144. So verify these 5 integrals. You must get exactly the same answer. If you compute correctly, you must get exactly the same answer. Next example, rewrite the triple integral in 5 other orders. The outer integral is from negative 1 to 1. The middle integral is from x squared to 1. The inner integral is from 0 to 1 minus y. F of SYZ. The integrand is f of SYZ. dz, dy, dx. Rewrite this triple integral in 5 other ways. In order to rewrite the integral in 5 other ways, we need to first of all draw the solid region in which we're taking integral. We must draw the solid region first. We must draw the solid region in which we take integral first. So for the solid region, the inner bound is z equal to 0, z equal to 1 minus y. Z equal to 0 is an SY plane. Z equal to 0 is an SY plane. Z equal to 0 is an SY plane. Upper bound is z equal to 1 minus y. How it looks like. Z equal to 1 minus y. That's an upper bound. In this equation, x component is missing. So we can draw this a line segment z equal to 1 minus y in the yz plane first. That's a line segment z equal to 1 minus y in the yz plane. Let's draw a line segment first, then we'll make a plane later. That's an upper plane. That's an upper surface. Let's draw a line segment first. We'll make it a plane later. Now, next, this is the projection in the SY plane for an outer integral. That's the projection. That's the projection in the SY plane. Lower bound in the SY plane. In the SY plane, lower bound is y equal to s squared. Lower bound is y equal to s squared. Upper bound is y equal to 1. That's upper bound. So that's a line segment that goes through 1 in the y-axis. That's lower bound. That's upper bound. X is from -1 to 1. When y equal to 1, x is -1 to 1. That's region D. That's the region D in the SY plane. That's the projection of the solid in the SY plane. So let's draw this parabola in the SY plane first. Let's draw this parabola in the SY plane. That's region D in the SY plane. Next, we try to draw the surface. Z equal to 1 minus y. It looks like this. That's the solid in the SY plane. That's a solid. That's a solid in which we take integrals. So that's the psi curve. The psi curve is this paraboloid cylinder. The psi curve is the paraboloid cylinder, y equal to s squared. The curve on the surface on the psi is the paraboloid cylinder, y equal to s squared. The cover on the top is the plane, that z equal to 1 minus y. Let's first of all try to switch order for y and for s and y first. That's the easy, simplest way. Let's first of all keep z the way it is. Switch order for s and y first. if we switch order for x and y, so the z bound stays the same. If we switch order for x and y, we try to take integral from left to right. So from left to right, we must write the left side curve and right side curve as function of x in terms of y. We have y equal to z squared, y equal to s squared. If I write x by itself, s could be negative radical y, and s could be positive radical y. That's the left side curve. That's the right side curve. Projection in the y-axis, y is from 0 to 1. So x is from negative radical y to positive radical y, from left side curve to right side curve. Projection in the y-axis, if I push the entire graph, entire region into y-axis, I have a line segment from 0 to 1. That's one different width. Next, let's try to consider this is a type 2 solid. Let's try to consider this as a type 2 solid. For type 2 solid, we try to find out the left side surface and the right side surface. Try to find out the left side surface and the right side surface. Left side surface here, we can see that left side surface is this paraboloid cylinder. Left side surface is this paraboloid cylinder. Y equal to s squared. For left and right side surface, we must write y in terms of x and z. For left and right side surface, we must write y in terms of x and z. So the paraboloid cylinder is the left side surface, which is y equal to s squared. The right side surface is this plane. The right side surface is this plane. If I try to write y by itself, I can write y as 1 minus z. I can write y as 1 minus z. So it can be written as, if I consider this as a type 2 solid, it can be written as y from x squared to 1 minus z. Left side surface is a lower limit. Right side surface is the upper limit. Integrand stays the same. F of syz stays the same. dy. Take double integral over region D, dA. D is the projection. D is the projection in the xz plane. Region D is the projection in the SC plane. Region D for type 2 solid. Region D is the projection in the XC plane. How is the projection looks like? For projection in the SC plane, this point become 1 in the x-axis. This point will become negative 1 in the x-axis. The projection, the projection for this line will be a line here. So the projection in SY plane is this region here. It's this triangular region. Projection in SY plane, in SC plane, is this triangular region here. In XZ plane, projection in SC plane, this point goes to 1 in the x-axis. This point goes to negative 1 in the x-axis. This point is 1 in the z-axis. Now, the projection for this line, is this line a curve or straight line? Projection for this line, is this a curve or straight line? How can we tell? Is this projection a curve or straight line in the SC plane? How can we tell? Is this line become a curve or straight line SC plane? How can we tell? So we know that this line is the intersection of the paraboloid cylinder and the plane. This line here is the intersection of the paraboloid cylinder and the plane y equal to 1 minus z. Since this line is the intersection, it must satisfy both equations. If we try to find out the projection in the SC plane, we must set this equation equal to each other. Set this equation equal to each other. We have s squared equal to 1 minus c. If we set these equations equal to each other, we have s squared equal to 1 minus c. If I solve for z equal to 1 minus s squared, it's a parabola open downward. It's a parabola open downward. Z equal to 1 minus s squared. It's not a triangular region. It's a paraboloid. It's an upside down parabola. So projection for this line in the SC plane is a parabola open downward. It's not a triangle. It's a parabola open downward. Same thing on the other side. It's a parabola open downward in SC plane. So that's a parabola open downward in SC plane. This is a projection. This is a projection in the SC plane. That's region D in SC plane. That's region D in the SC plane. This curve is a parabola z equal to 1 minus s squared. So lower bound is s-axis, which is z equal to 0. Upper bound is z equal to 1 minus s squared. Upper bound is a parabola z equal to 1 minus s squared. Then, if I push the integral graph down to an s-axis, I have a line segment from -1 to 1. So x is from -1 to 1. Integrand stays the same, f of syz dy dz dx. That's a different way to set out an integral. Next, let's consider another way to set out an integral. Another way, I keep y the same, but in region D, I change the order for x and z. In the previous method, I integrate from bottom to top. Now I try to integrate from left to right. If I integrate from left to right, I must write x in terms of z. If I integrate from left to right, I must write x in terms of z. If I solve for x, s could be either positive or negative radical 1 minus z. So the left side curve is s equal to negative 1 minus z. That's the left side curve. S equal to negative 1 minus z. Right side curve is s equal to positive 1 minus z. So x is from left to right. In the integral, y stays the same. F of syz dy dx. Now, for the boundary for x, for z, for the boundary on the z-axis, if I push the entire region into the z-axis, I have a line segment from 0 to 1. So boundary for z is from 0 to 1. That's a different order. dy, dx, dz, that's a different order. Next, let's consider this solid as a type 2 solid. Let's consider this solid region as a type 2 solid. Next, let's consider this as a type 2 solid. Let me draw this solid over. So that's the solid. The side curve is the paraboloid cylinder, y equal to s squared. The plane on the top is z equal to 1 minus y. That's this plane, z equal to 1 minus y. This is 1 in the y-axis. This is 1 in the z-axis. Now, consider this as a type 2 solid. We try to find a surface in the front and surface in the back. For surface in the front or back, we write x in terms of y and z. So for this picture, you can see that this is a surface in the front. This is if you look at the graph, this direction. If you look at the solid, this direction. This is the surface in the front, and the other half paraboloid cylinder is a surface in the back. The other half paraboloid cylinder is the surface in the back. So the surface in the for the surface in the front and back, we try to write x in terms of y and z. So the front surface is x equal to radical y. The back surface is x equal to negative radical y. So I can set out the integral as x from negative radical y to radical y. The back surface is the lower limit. The front surface is the upper limit. So this is the lower limit. The back surface is the lower limit. Front surface is the upper limit. F of s y z integrand stays the same. Dx. Then take double integral over the projection d. D is the projection in the yz plane. D is a projection in the yz plane. So in the yz plane, this point will go to 1. This point also goes to 1. So the entire parabola goes to this triangle. The entire parabola will be projected to this triangle. So the projection in the yz plane, is this triangle. Projection D in the yz plane is this triangle. It goes through 1 in the y-axis. It goes through 1 in the z-axis. I didn't draw this triangle in scale, but this is a triangle in the yz plane. This is region D. This is region D here. This triangle is region D. That's the projection of this entire solid in the yz plane. If you look at the picture in this way, all we can see is this surface. This surface will completely cover this triangle here. So that's the projection. We only see this half surface. That's the front surface. We don't see anything else. So that's the projection. The back surface is this half paraboloid cylinder. It also, if I push the entire graph into the yz plane, both surfaces will go to this triangle, will be mapped to this triangle. So that's the projection in the yz plane. Now, if we integrate for region D, if we integrate from bottom to top, lower curve is z equal to 0. Upper curve is this line. This line is z equal to 1 minus y. This plane is z equal to 1 minus y. We can use it here, or we can find it by ourselves. A line going through point 1, 1, we can find it by ourselves. Y-intercept is 1. Slope is negative 1. We can find it by ourselves, or we can use the equation of the line. We can use the equation of the plane. So, in the integral stays the same. S equal to negative radical y, s equal to positive radical y. F of s, y, z dx. Next one is z equal to 0, z equal to 1 minus y. dz. The outer integral, if I push the entire region D into the y-axis, if I find a projection in the y-axis, I have a line segment from 0 to 1. So y is from 0 to 1. dx, dz, dy. Y is from 0 to 1. So that's a different way to write the integral. For another way to write the integral, I try to switch order for y and z. For another way, try to switch order for y and z. In the previous method, I integrate from bottom to top. Now I try to integrate from left to right. Now I try to integrate from left to right. From left to right, I try to write y. I try to write y in terms of z. Write y in terms of z. This line is y equal to 0. If I get y by itself, this line is y equal to 1 minus z. So the inner integral stays the same. X is from negative radical y to positive radical y. Left bound is a lower limit. Y is from 0 to 1 minus z. Y is from 0 to 1 minus z. And if I push the entire region D into the z-axis, I have a line segment from 0 to 1. So z is from 0 to 1. F of s, y, z, dx, dy, dz. That's a different way to write the integral. So we have a total of 6 ways to write integral. That's one of the way. Based on this way, I can write 5 other. That's one of the order. Based on this order, I can write 5 other orders. 1, 2, 3, 4, 5.